So before we get into working with collisions in two dimensions, just to recap a couple things that have come up in the concept questions, like this one. I believe this is one of the ones I gave you. If not, it illustrates my point. So finding the direction of the impulse comes up. And what I want you to understand about this is that direction of the impulse is the change in momentum. So if we take a look at A. Now A's beginning momentum is this. It's about that long, right? So it works for me. Now that is 3 meters per second times some mass. So since all the masses are supposed to be the same, let's go with 1 kilogram apiece. So that would give this a momentum initially of 3 kilogram meters per second, positive to the right. And then this case, it's going to the left later on. So maybe it bounced off of something and was sped out, hit by something. It doesn't matter how. All we care about is that afterwards, after some external force, notice in this case we have to look at it as external, we have 7 kilogram meters per second, assuming our object is 1 kilogram. But it's negative because it's going to the left. So if we called this positive, then this way here has to be negative. So let's do this. Let's make this arrow blue for illustration purposes. So I have a blue one and this one. And we'll trust the publishing company that their errors are the length they mean and that they're to scale. So here's what we do. We take our beginning and our ending momentums. Whoops. Did it again. Just want this. I'm getting frustrated. I don't even know how I did that. That's impressive. There we go. And we line them up so that their bases, their tails, are touching each other, like so. And then we just draw a line from the tip of the initial momentum vector to the tip of the final momentum vector. So in other words, this line. Because that goes from where our momentum was to where it is. This represents wow, this is frustrating. So apparently my smartboard sucks, but you didn't need me to tell you that, did you? There. Whew. Wow. Okay, so the change in momentum is represented by this black arrow. That's your change in momentum. It would be directed to the left. So for A, S would be the best direction. This is the direction of your change in momentum. Let's use that same idea for, let's see, let's do C. So let's go with 2 momenta. Maybe this will work better. Been acting up recently. So one of them looks like, oops, that was my fault, this. And the other one, that's your beginning momentum. That's a vector representing that. This represents your ending. And so what we have is the following. I have to find some space to do this. Hopefully it'll grab it. There we go. It's successfully done. And then, yes. So we line them up like so. Their tails touching like that. And then we draw another vector from the starting at the original momentum's vector tip to the final momentum vector's tip. So it goes from here to here. So your change in momentum for C is going to be this vector here, which is most nearly T, I believe. So try the same thing for the other two. I think if you keep it straight that way, go from the tip of the initial momentum vector. So here's your initial momentum vector. From that tip to the tip of the final momentum vector, that will give you your change. Also, you can look at it as if the velocity changed by that amount, that's also the way the net force has to be pushing. In order to get this from going this way to this way, my force has to do two things. A single force would have to push in such a way so that it would have an x component that would cancel this completely, eventually, and at the same time a y component that would get it started moving in that direction. So your net force would be this, and of course your impulse has to be in the direction of your net force, because impulse is force, net force times time. Your average net force times time. All right, moving on. So some collision practice here. Not two-dimensional yet, but the cards collide. They're the same size and shape, but they have different loads, traveling at different speeds. So the speed of the two-cart system. So first thing we need to do is find all of their initial momenta. So, for example, what's the initial momentum for A? Because that's going to have to be equal to the final momentum. Well, that's going to be 500 grams. Well, it really doesn't matter, but 500 grams is technically 0.5 kilograms. So 0.5 kilograms. Now they do centimeters per second. Okay. I don't think it's going to make a difference. We'll just keep the units that they have instead of changing them because it's a conceptual question. So for A, you have two momenta beforehand. We'll do 500 times 20, positive, going this way, minus 400 times 25, which is going to give us, let's see, 10 with 3 zeros, minus, this is going to be 25 times 4, that's 100 with 2 zeros. Okay, so we have a situation where the combined momentum in this case is 0. So if that's the initial momentum before the collision, of course, that's got to be equal to the final momentum, which is 0. But after they collide and stick together, that means the one object has to have a 0 momentum. Well, the object will be 900 grams, but the only way you can get it to have 0 momentum is to multiply it by 0. So the final velocity of A has to be 0. And we do a similar process for all of them. So let's see if we can find one that doesn't add up to 0. Here, we would have a positive, let's see, 2 times 4 is 8, plus 3 zeros, 8,000, and a 10 times 8 is 80 with 2 zeros. Same deal. So 1 500. So this is going to have a 0 initial momentum, and therefore, if they collide and stick together, the final velocity has to be 0. So this has a final velocity of 0. So does this one. Let's see about this one. Well, almost certainly, right? Because they're same mass, same velocity going at each other, so I can tell you the same thing. Final velocity 0. Let's see. 8 times 2 is 16 with 3 zeros after it. 4 times 4 is 16. So it looks like all these are going to have 0 with 3 zeros after it. Yep. So all of them are going to have final velocities of 0, as it turns out. Because all of them are going to have, after they stick together, before they have 0 momentum for the system, afterwards they're going to have 0. But if you're stuck together in your one object, the only way to have 0 is that you're not moving. if you had a leftover momentum for any of these, if they hadn't come out to be final momentum or initial momentum 0 and therefore final 0, if it had been some number, you would have divided by the total mass to get the velocity, but not necessary in this one. I know this is one of the ones I assigned, so what letter best represents the direction of the initial momentum of ball T? So I wouldn't overthink this. We've got ball T has an initial momentum of this and a final momentum this way after the collision, whereas ball S has an initial momentum, this direction. I got to move that. Whoops. There we go. And a final momentum directed out this way. So what letter best represents the direction of the initial momentum of ball T? I would say D. That's the direction of its velocity coming in. That's the direction of momentum. That's the velocity vector that determines the direction of the momentum. Which letter best represents the direction of the final momentum on ball T? I think B is the correct answer there. Ball T goes out like this. That's B. Once again, direction of the velocity. Which letter represents the change in momentum for ball T? So, let's just double check. First of all, it comes out, speeds of the ball is the same. So they have the same magnitude of momentum, but the directions are going to be different. So for ball T, for example, its initial momentum was, say, like this, and its final was like this, but I'm not going to draw it I'm not going to put it like that, same magnitude. I'm actually, to figure out the change in momentum, if you recall a couple of slides ago, I'm going to put them so that their tails are like that. And notice, granted, I think I draw this one a little better. Boom. Notice that the change in momentum turns out to be vertically. Interesting. So this would be my explanation here, but let's add to that. If you think about it, when the ball comes in, hits, and then goes out, it maintains the same horizontal component to its velocity the whole time. Even that instant when it collides. This never changes. So the x-coordinate of the momentum, and now we're starting to look into two dimensions, the x-coordinate of that momentum, the x-component, I should say, of that momentum, is the same. But the y component gets changed because it did have a y component of its momentum initially that was this way, and then the external force by the other ball changes that, and now its y component, its final y component's that way. So all the change in this case occurred in the y. And that change took it from going this way in the y to this way in the y, so the change is, as we see it, it's vertical that way. But no change in the x. So what we want to keep in mind here is we're starting to look at the component nature of momentum. So the change in momentum for ball S, we're going to have ball S's initial momentum, we'll say, is like this coming in, and its final is like that leaving, but the same length arrow. But in order to find that change in momentum, I'm going to line up their tails, and what do you know, from the start to the end, the change in momentum is straight down. That's because, same reasoning as before, that the momentum, the original momentum for the S ball, in the X is constant. It's the same. It's the same as the final. Because the force of impact does not affect, there is no net X force. But the y definitely changes. In the y dimension, the original y momentum is upward, and after the collision, the y component is downward. And so that's why this change is downward. To say which letter best represents the direction of the change. And so I guess if we had to give letters, the one I just did is E. And the one up here would be A. Which letter best represents the direction of the impulse on bite? Well, impulse is the change in momentum, so it would be the same as letter C, which would be A. Impulse is another word for change in momentum. All right, two balls traveling in different directions are about to collide. The balls are identical in size and shape, but they have different masses and traveling at different velocities is shown. So, what I know from conservation of momentum is this, is that the momentum of the two ball systems before they collide. Okay, so we're going to take a look at these. And by the way, that is going to be the same as after they collide. If we look at the system of just those two balls, then whatever we answer here is what we're going to answer here. That's conservation of momentum. That would be my explanation down in here, would be conservation of momentum. So what are those? Well, in this case, I've got a momentum of this ball of, we'll call it ball 1, is going to be 3 times 2 is 6 kilogram meters per second. This one's going to have 8 kilogram meters per second. So I have a vector, two vectors. Adding these two, since they're at 6, we'll call this 8. I got to use Pythagorean's theorem and all that. So I got the resultant of those two is going to be that. So this is your initial momentum total for the whole thing, which is going to be square root, the magnitude of it, of 6 squared plus 8 squared. So the magnitude for A, this is all for situation A, is going to be 36 plus 64. That's 100. So square root of 100 is 10. How nice of them. Notice you're not just adding the 6 and the 8. Right. 36, 64. Just add them. Yeah, that's right. Sorry. Okay, so here I have 8 kilogram meters per second and 6 kilogram meters per second at right angles to each other. So in situation B, I have a similar situation. I have 8 down and 6 this way, but I still end up with the same value, the same magnitude, because it's the same right triangle. It's going to be 8, 6, and 8 squared, 6 squared, just like this. So I'm still going to have 10. Here, well, I got identical momenta, but they're in opposite directions. This is, we'll call it positive 8 kilogram meters per second. This is negative 8. Notice this is a one-dimensional situation. All the motion is in one line. So the total momentum here at the start is 0. This one is, let's see, we have going to the right, that's going to be 6 kilogram meters per second positive. Once again, this is a one-dimensional situation. This is going to be negative 9 kilogram meters per second. So the magnitude here, well, the original momentum would be negative 3 kilogram meters per second. But they just want magnitude, so we can just say 3 kilogram meters per second. Can you tell I'm tired? So I got 10, 10, 0, and 3. So we'll go A and B here, and D followed by C, which has 0. Remember, they want magnitude, so I'm going to ignore the negative. And whatever I answered here is what I'm going to answer here, because the final momentums have to be the same. It doesn't matter really if they stick together or not, to be honest with you. The final momentum of the system has to be the same in a collision where it's all the forces are internal.